Hi there. These slides are going to help you to understand how to carry out conservation of energy Q calculations. This will be necessary in order to identify the metal that you had in the specific heat lab. Let's revisit the concept of conservation of energy. Let's say that I had a piece of metal that I had heated up, and then I placed it into a beaker of room temperature water. What would happen? Which way would the energy be transferred? Now let's assume that for these purposes that this is a closed system. Hopefully you thought that energy would transfer from the metal to the water. By placing the hot metal into the water, it would warm up the water, and so energy would flow out. Now, still thinking about this idea of conservation of energy, let's say there's a certain quantity of energy lost by the metal, and there's a certain quantity of energy gained by the water. What symbol would work in this box? Is the energy lost by the metal less than that gained by the water, equal to, or greater than? Hopefully you understand that assuming this is a nice closed system, the energy lost by the metal would be equal to the energy gained by the water. That first law of thermodynamics states that energy cannot be created or destroyed, but it can be transformed and transferred. So therefore, we will assume that the energy that's lost by the metal is the same amount of energy that's gained by the water. So in this specific heat lab, we're going to use this idea, this law of conservation of energy, in order to calculate the specific heat of an unknown metal. This would be the C value in our equation. First, we'll collect the data, then you'll learn how to carry out the calculations. So now we'll carry out the lab and collect data, so we'll pause here. You can pause the video or just keep going if you already have your data. So now let's apply our data to the actual lab. And what you'll remember is we heated up a water bath, and we put our metal inside of that water bath and let the metal's temperature basically equilibrate with that of the boiling water. And we will assume that the initial temperature of that hot metal is the same as the water, which would be 100 degrees. We also obtain the mass of that metal, and then we place that hot metal into our calorimeter, and we had obtained the initial room temperature of that water. We let the metal sit in there and we watch the temperature rise until it stopped rising. That is the final temperature of both the water in the calorimeter and of the piece of metal. So now, getting back to the calculations. Remember that because no energy is lost out of our system, if it's a perfect system, the amount of energy that's gained by the water added to the amount of energy lost by the metal should be zero. In other words, it went directly from the metal into the water. So there should be no difference. Therefore, we can assume that the energy gained by the water is equal to energy lost by the metal. So that's why the second Q is negative, because that's exothermic, the metal's losing energy. So we're going to calculate this as instead of one big equation, two simple steps. So the first step is to calculate the energy gained by the water in the calorimeter, in the cup. And we will then use that answer, which will be a Q value, in order to calculate the specific heat of the metal that we don't know. So we'll first solve for Q of our water, and then we will solve for C of the metal. Here we have some sample data. These may not match your data, but hopefully they will help you to work through the problem. So let's walk through it. In yellow on the left, we have the mass of the water. Now this is the mass of the water in the calorimeter. And we have the initial temperature of the water in the calorimeter, which was approximately room temperature. These first two values would have been gotten before we put the metal in there. We also know the specific heat of water, liquid water, 4.186. On the right, we have the mass of the metal, which we obtained before putting it in water, The initial temperature of the metal is going to be after it sat in the boiling bath for about 10 minutes so that it would reach 100 degrees Celsius. Then we transferred this metal into our calorimeter and let that water temperature rise in the calorimeter. And in this case, it went to 21.4 Celsius. So notice that the final water temperature for both the metal and the water is the same. So what we don't know is how much energy did the metal give up. That's what we're going to figure out. So, and remember, the amount of energy lost by the metal is equal to the energy gained by the water. So let's figure that out first then. We are going to find Q. We are going to need the mass of the water, specific heat of water, final temperature of water, and initial temperature of water. Well, these are all values we have. Here's our mass, here's our specific heat, here's the final temperature of the water in the calorimeter, subtracting out the initial temperature of the water. Put all those units in there so you can see what cancels out, and this would leave us ultimately with 264 joules. And so what that means is the metal transferred 264 joules of energy to the water. If you need to pause here to carry out this calculation yourself, go ahead and do so. But now we can use that information to figure out the specific heat of the metal, because remember, the energy gained by the water is equal to the energy lost by the metal. So still is Q equals mc delta T, but now we have a negative Q because it's energy lost. But see, we know this. We just figured it out on the previous step. So that would be a negative 264 joules. We know the mass of the metal. We don't know the specific heat of the metal. That's actually what we want to find out, because that would identify which metal we have, since it's a unique property. We know the final temperature of the metal and the initial temperature of the metal. So if we reorganize this equation to solve for C, this is its setup. Negative Q divided by the mass times delta T. And if you need to pause to do this algebra yourself so that you understand that, please do. So now we'll plug in those values. Remember, this is a negative 264 joules because energy was lost by the metal, divided by the mass of the metal. And here's the metal's final temperature and its initial temperature. Notice that the initial temperature of the metal, it was 100 because it came out of that hot water bath. So once you do all that math, you come up with 0.13 joules over grams times degrees Celsius. Now, all those units need to be in your work so that you can see that you've done your math correctly to give you all of the units that we would find in a specific heat value. Okay, so we have this 0.13, but what does that even mean? How do we know what metal it is? In this case, then we would give you a reference sheet and you would see how close your answer was to a known metal specific heat. So here's a table with some metals, a handful of them, and their various specific heat capacities. And so as you can see, 0.13 is pretty close to lead. And that's the closest one we have on this table. Ours is not going to be exact. Think about the kind of sources of error you would have. Was it really a closed system? Were you as quick as you should have been in transferring the metal? What other areas could we have had an issue with that may not give us a really great specific heat value? So now that you've done that, you should be able to carry out your calculations and then identify your metal.